Yes, recording is in. Can I start now? Huh? Good morning, my dear friends. So, due to the lack of proper networking, we are unable to interact directly. So that I am making the video clips here. Yesterday, in the last class, we derived the de Broglie's wavelength and expression for the de Broglie's wavelength is completed. Dual nature of light is also completed. So under the dual nature of light, so the properties of the electron or the property of the body particle, so like momentum and the position, so we cannot determine exactly within the packet that I yesterday discussed with you. So the imaginary envelope means the number of waves are superimposition to a particular area. So that will form the packet that is called a wave packet. Within that wave packet, for example, look at the picture here. Here picture is there, which you go through this picture. So for example, I will take here, what is this pencil? Where is it? Yeah. So see, this is the wave packet. Yeah. Pencil. Okay. So look at the pen here. So this is the boundaries of the wave packet. This is the boundaries of the packet. First boundary, second, last boundary here. So this first wave, second wave, third wave, fourth wave, fifth wave, sixth wave is there. So so single wavelength you are going to indicate that is only wave packet that like this equal to one wave. Okay. For example, particle is here, 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 or here or anywhere that is within the wavelength wave packet only. So this is there. So condition is what? So according to the de Broglie's hypothesis, okay, lambda is always inversely proportional to its momentum. That is lambda is equal to h by p. You know, okay. With the help of that, we can think that we can write, we can assume that. So delta p is large. This means momentum is large. Its position is very small. For example, you take here, okay. The delta x wavelength is very small, but we will consider that inversely proportional to that momentum in delta p is large. Why I took here delta p and delta x instead of p and x? You know that p means exact momentum of the particle, delta x means there is not an exact position momentum, therefore delta I am applying here. Delta x is there, so delta x means so uncertainty of the position. So with the help of that, so we can conclude that delta p is small means delta x is large, so inversely proportional to each other. Okay. Now, now, so yesterday we completed the Heisenberg uncertainty principle, or the we can call this is the application of Heisenberg uncertainty principle. What we find? So for example, take one pencil. Where is the pencil? See. So for example, this one round circle is can I take this? For example, take one circle like this circle. So within this circle, okay, if electron is here, it may be in the radius. Therefore, I use the formula for maximum position of the electron is within that radius only. What radius we have defined? What radius if it's fixed? What radius we defined? Okay. For example, 20 centimeter of radius in all, okay, in a circle. So 20 centimeters there means, for example, this is the radius, okay, this is the complete radius. Here, wherever the particle is there, okay, for example, wherever the particle is there, it should be within the radius only. Therefore, maximum electrons, okay, wandering or the rotating or the placing or the locating or finding, the probability of the finding the particle is within this nucleus, means it is within the radius only. It means maximum chance chance of position of electron is equal to its radius only. Therefore, it is not fixed. Therefore, delta r, okay, delta r or delta x I will take, okay, the radius equal to its maximum position. When you know the maximum position, you come to the formula of Eisenberg uncertainty. What is the Eisenberg uncertainty principle here? So that, wait, what is the Eisenberg uncertainty principle here? So that delta x into delta p equal to h by 4 pi. So delta p I kept as it is, and delta x I took here. So substitute all values what we know, okay, constants, then you will get the values of this, okay. Now, by the relation, fundamental relation, okay, relative, wait, yeah. So by the theory of relativity, so we know the fundamental equation. Look at the cursor here. See, E is equal to P square divided by 2m is the fundamental equation is there. So we know the energy. So this energy is the fixed energy or uncertainty energy of the electron. Will find it. Okay. The values we what P square by 2m is there. P square means it is a fixed momentum, but we are not going to discuss here fixed momentum, exact momentum, because we are discussing only uncertainty values of momentum, that is delta P. Therefore, we assume that the uncertainty momentum is also equal to the momentum only. So that we, by keeping the assumption point, so delta P is equal to, I substitute the values, whatever delta P, this value. So I will substitute here, and m is mass of an electron. The mass of electron is constant, 9.1 into 10 to the power minus 31 is there. So substitute all, you will get this value. Now, so you will get the 95.45 into 10 to the power of 10 plus 10 electron volt. Okay, how you got this is, this value by substituting this value, by simplify from your calculator, you will get 1.527 into 10 to the power minus 11. Whatever energy you are getting by calculating from the radius of electron, its value is in joules. Okay, you convert this joule into electron volt, means divide that value divided by coulomb. What is the charge of an electron? 1.6 into 10 to the power of minus 19. If you divide that, means then you will get the values of mega electron volt. Okay, here he missed to write here 13 he wrote, so it is a misprinted. That is, you take this is the 10 to the power minus 19 only. So by that you will get the values. For example, you will check it here. If this is the minus 19, this is the 11, means the 11 plus 19 means it will be the plus 7 only. So you divide, it means you will get, it will come the value 10 to the power plus 6 only. Plus 6 nothing but it is a what we call, this is a what we call mega only, mega of the 10 to the power plus 6. Okay, so that you will get. Now the question will arise here, another one. What is that? So our heading is whether electron exists in the nucleus or not. Okay, for that, so according to the fundamental beta decay, what we studied in the previous years before the COVID, what we studied. So in the from the 8th standard onwards, from the beta decay, from the beta particle emitted from the material. So that electron has, or that electron does not exist more than 4 to 5 or 3 to 4 mega electron volt. Remember, the maximum electron energy is 3 to 4 mega electron volt. Then only it exists in the nucleus. But here, the electron what we have here, according to the radius of this nucleus, diameter of the nucleus, we got 95 something mega. It means it does not exist because its value is more than that. Whatever the capacity is necessary, it is more than that. Therefore, summarily will reject that. What we write to conclusion point? For example, if you say that the electron exists in the nucleus, means it should be okay value or the space or the maximum electron energy should be 95, but here 95, but the fundamental experimentally it is not true. Experimentally is what? It is not exceeding 3 to 4 only, therefore it does not exist in the nucleus. This will complete you 10 marks. Okay, very easy. Okay, I will summary here once again within 1 minute. Consider a nucleus, consider a nucleus and consider a electron wherever you want to put here. So you assume that electron chances or maximum its diameter or its radius, that is the position. Then you know the formula, substitute the values, you will get the values. Okay, so this will complete your applications of uncertainty Heisenberg principle. So now come to another one. Okay, here here we are going to discuss another bit is wave function. What do you understand the wave function and what are the properties of this? What are the limitations of that? Before that, wave function is what? For example, see that continuously variation is there. This is a particle, but this is a particle. The continuous variation of the particle. It means up and down, up and down, up and down, up and down is there. This, for example, this is a quantity. Which quantity? Variable quantity that characterize the de Broglie's wavelength. Characterize the de Broglie means you know the de Broglie wavelength is what? De Broglie's wavelength is lambda is equal to h by p. According to that statement, lambda is always inversely proportional to its velocity and inversely proportional to its mass. By this value or the matter make up of a quantity, periodic variation. So that periodic variation of the quantity is known as a wave function. So that will write in the physical definition like that. You look at the picture, the variable quantity, this is a variable quantity that characterize the de Broglie's wavelength. It means it must characterize its value of de Broglie's wavelength. Let it lambda by lambda is equal to h by p of that particle. This is called wave function and is denoted by a symbol sign, Greek symbol sign. Okay, this is a called here PSI is there. P you will take the silent, then you will write or read sign. This is the value. Mathematically, the wave function psi can be described in the motion of a particle. So like that only. For example, this is the body. Okay, now one bubble is there. See, one bubble, it is moving up and down, up and down, up and down, up and down. Look at the picture here. Okay, the particle is moving. You are going to define, you are going to analyze with the help of mathematical induction. Okay, for that you are giving the mathematical notation, that is the sign. What sign is the wave function? Particle, it is moving periodically, the variable quantity is there. That's it. Okay, it means this wave function is depends upon the space and the amplitude and the time. Okay, how much space it's covered, how much time it takes, and how much amplitude, maximum displacement it will go to propagate from one point to the another point. These are the concepts are there for the wave functions. Therefore, it depends upon these three fundamentals are there: space, momentum, and the amplitude and the time. Whatever required properties are there, I will take to discuss in the wave function. So what are the properties of for this? Remember first, okay. For example, here one particle is there, particle is moving, okay, from one point to the another point in the form of wave. Okay, in the form of wave. So up and down in the form of wave, the particle is moving. Are you able to see the pen? So in the pen, so you think that this is the wave packet. Inside the black is there, there is a shut off waves, superimpositions of number of waves are there. So in that, particle is moving, in that the particle is moving. Okay, sir ನಮಸ್ಕಾರ ಹೇಳಿ ಸರ್. ನಮಸ್ಕಾರ ಹೇಳಿ ಸರ್. ಸರ್ ಕಾಲೇಜ್ ಇದ್ದೀನಿ ಸರ್, ಹೇಳಿ ಸರ್. ಯಾವ ಸರ್ ಅಮೌಂಟ್ ಅಂತ್ರಿ? ನಾನು ನೋಡ್ತೀನಿ ಸರ್, ನಾನು ಮಾತಾಡ್ತೀನಿ ಕ್ಲಾಸ್ ಮುಂದೆ ಮಾತಾಡ್ತೀನಿ. Sorry. So this is the wave, how to define the wave, then how to call this is wave by the help of time, space, and the momentum is included in this property. That is called wave function. Okay. So first property is what? If you find the wave function is single value, okay, wherever you are going defining, so that value will be single only. Here is single, 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 single. For example, it is a three-dimensional space is there. Three-dimensional space is there. For example, this is the three-dimensional space. Wherever you will find here, the x-axis, y-axis, z-axis. The value once it is defined a single value, wherever we will define it is a single value. First property. Second, it is a finite. It is a finite means it is a positive. Remember, it is a finite value. Why positive? I will discuss once again for this fundamental. Okay, but finite means plus 1, 2, 3, 4, 5. What is the definite value will be there? Okay, it is not infinite. Okay, finite value is built. Okay, then this sine wave function will be continuous. How, for example, here x-axis, y-axis, z-axis. Wherever you will find, according to that coordinate axis, it will rotate it. Okay, there is a continuous is there. And not only x component, y component, z component, the wave is continuous. You will take the derivatives of this. For example, dou psi by dou x means first order derivatives of the x-axis. Dou y by dou psi, second order, first order derivatives of the y-axis. Dou psi by dou z. This is the first order derivatives of z-axis. No, simply x, y, z. It is a continuous. Not only in the x, y, z, its first order derivatives vary or length or the direction also it is continuous wherever it is going to define in the space. That is remember. Okay, these are the some important properties you need to remember of this wave function. Second, what is the probability of finding the particle or probability density to find the particle? That is very important. See, always the probability of finding the particle, for example, saying is there means it is not a definite. Why not definite, sir? Now only you said that is a definite. No, when will make definite? I will tell no in the coming introduction part for that after 1 minute. Okay, in the physical significance of the what we call wave function, I will discuss that. So it must be a probability. Probability means, see, any one particle is here. If it is having positive, then you will get here. Yeah, this value is this. This value is this. There is a here. There is a 1 meter on the axis of 5th meter, 6th meter, 8th meter. If you don't know exact physical appearance of that particle, you cannot define. Therefore, if one is negative, another one is positive, another one is the negative imaginary. Positive, negative, imaginary is what, sir? For example, wave function is you are able to touch it, able to realize it in the x-axis. That is a positive. You are able to hear the sound, but you are unable to see that value. You are unable to find that physical values. Therefore, it is called as a negative value. It means the wave function is not measurable. That it is not a direct measurable quantity. It is a indirect measurable quantity. You make it into direct quantity. How, sir? For example, it is a negative means sound will come, but body will not appear. For that, you will make negative into negative and it will become positive. Therefore, not only negative, but it will include as a complex also. By some value, for example, sin is equal to a plus b, sin star means conjugate complex is equal to a minus b. If you sin into sin star, you will do it means sin square is there. You take within the modulus sin square. Why modulus? I don't want to recognize with the negative value. If negative value means we cannot measure. For making positive, the sin square is within the modulus. Therefore, the probability of finding the particle is always sin square. Why sin square means what? So a plus b, a minus b. If you multiply means it will remain only a square plus b square, where a square and b square are the positive, finite, and the values. Let's say n square or 1 values. So that is the another property or the finding the probability of the particle. For example, if you know the box, okay, this is the box from here to here. Okay, integration of 1 value to 2 or integration of 0 centimeter to 20 centimeter of this box. Okay, under the modulus of a sin square. Sin square why beta? Making the positive equal to 1. 1 way because all values should be positive only, or says n square. This is the probability of finding the particle. If this value, the boundary value is unknown, 0 and 1 is unknown. So how much centimeter initiated, how much centimeter it is end, it is unknown, it is infinite. For that, what you will write? Integration of minus infinity to plus infinity. Write sine square into dv is equal to 1. What is the dv, sir? This is the volume, space. Complete this. This is the v, capital V. Somewhere where you are finding the particle, x-axis, y-axis, that small element is dv. Small element dv. dv is nothing but dv is equal to, it may be dx or it may be dy or it may be dz. It means there is a change of direction. There is a change of direction along x, y, z. Nothing but dv is equal to dx, dy, dz. That will write. Instead of dx, dy, dz, we can write only dv only. So therefore, compression or complex of these values, minus infinity to plus infinity, modulus of sine square. Okay, go through the point here. Sixth point I wrote here is into dv. Here t square wrote, you consider only sine square. Okay, it is not going to give a confuse because some wave function I assigned here sine. Therefore, you will take the sine square only. This is equal to 1. So this is the probability of finding the particle. Okay. For example, only I want a dx or x axis be, sir. Only I want y axis, sir. Only I want z axis, sir. Means then you write clearly minus infinity to plus infinity sine square into dx. Sir, I want dy. You meant into dy. I want all, sir. dv. That's it. These are the some properties. You go through the points I sent here. Okay, this is the points. Now, what are the values here? Physical significance are there. It is given here. Satisfy the interpretation of the wave function sine, okay, associated with the moving particle was given by the Max Born. Max Born gave a statistic. What he is given, the wavelength is there. The wavelength is always inversely proportional to its mass. That's the same. So that the matter whatever is there associated with the wavelength of the particle. First one. Now the probability of finding the particle is what, sir? Second physical means. So it make the square of wave function sine into sine square under the modulus. So this is the second point or the physical interpretation for the wave function. Third one is that probability finding of the body is also called as a p is equal to modulus of sine square into dv. That's it. So next, if you want me normalization equation, you make normalization equation the same. Another that property also you can write the normalization equation. What is that? Same minus infinity to plus infinity under the modulus sine square into dv is equal to 1 or equal to n square is nothing but normalization equation. This is another one physical. Okay. So now any wave function that obeys this equation, this equation means minus infinity to plus infinity. That then only we called as a, this is the normalized wave function wherever you are going to find in the space. Okay. Remember, the normalized function must be finite. Must be finite means it should be sine square only. And the single value may be continuous anywhere within x, y, z value. So this will give you complete, okay, 2-bit question. One is properties of wave function, another one is the physical significance of the wave function. I will summary once again. I will summary here. What is the physical significance? What is the properties? Okay, very easy. Physical significance is what? Sir, we cannot determine wave function, sir, here because sometimes it is negative, positive, or the imaginary, sir. Therefore, you cannot determine directly. How you can make directly? Sir, make it a positive, sir. Negative into negative. Or you take the a plus b and a minus b. Sin is equal to a plus b, sin is equal to a minus b. Comprise it. It means complex it. It means product it. Sin into sin, that is sin square. That sin square value will be positive only. I will give that theory part also. Why it is means you nothing is there. A plus b into a plus ib. You square it. You solve it. You solve it, you will get the values only a square plus b square. Sometimes it may come I square. The I square value also always it is a -1 only. Therefore, you will get back. Okay, I will give that fundamental also. The what you 8th class you studied. Okay, a plus b into a minus b. Okay, by multiplying what equation you will get, that also I will send the notes for that. Okay, so this way physical significance is writing value. Properties, wherever you will find infinite value, this is a finite only. Okay, probability is sin square into dx only, and first order derivatives also is continuous as like the normal along with the x, y, z, the particle is continuous. So these are the some properties you need to remember. Okay, now we will come to next one. Now we will discuss the Schrodinger wave equation. What do you understand by Schrodinger wave equation? For example, see, you know that when we have the wave along with the x-axis, along with the y-axis, along with the z-axis, okay, this is the, or you take these three axes, okay, these three axes, okay, yeah, these three axes, x-axis, y-axis, this is the particle, okay, this is the particle on the y-axis, or you will take a, see, this is the particle on one axis, okay, y-axis, y-axis, this is z-axis, like that, okay. X, y, z movement is there, particle movement is there, or one dimension is only one dimensional or one axis, it will move, the particle is there. Now, the Schrodinger wave equation, okay, the fundamental or the mechanical wave, it has a solution. That solution for the fundamental mechanical wave for the particle in one dimension, what we are getting, that equation we call as a Schrodinger wave equation, okay. So how many types of Schrodinger wave equation is there? There are two types of Schrodinger wave equation. One, the body is moving, the particle is moving along with the x-axis, for example, x only. The particle is moving along with the wave, okay, in this wave packet, okay, moving, okay. This is in the x-axis. That is called one dimensional is there. Now, when it is moving means it is having some mass, it is having some velocity, all is there, okay. Its angular frequency is there, amplitude is there, all value, fundamental values are there, okay. Now, the important things we are going to discuss for your syllabus, there are two types of Schrodinger wave equation. One is time dependent, another one is the time independent. Okay, what is time independent, time dependent? Very easy. So when time dependent, nothing but the wave function or the sign value is depends on the space, means x value, as well as the time t value. Another, that is called time dependent. Time independent, okay, there is no depend, there is not depend on the time, it is depends on only position, that is called time independent equation. So these are the two Schrodinger wave equation we will discuss. So according to your syllabus, we are having only time independent Schrodinger wave equation, not a position dependent, position dependent, okay. Time independent, okay. Time is not discussion here, okay. That will discuss in the coming class, okay.